All right, so we're going to continue section 11.6, and we're going to start off with a couple of examples. So we're on page 747. We're going to do number 10. Number 10 says, find parametric equations for the line that passes through 2, -1, 0, and is perpendicular to the plane 2x minus 3y plus 4z equals 5. So one thing to be cautious of in this section and in general, like whether you're taking a test or doing a homework or suggested problems, is pay careful attention to, are you being asked for the equation of a line or the equation of a plane? So we're in the plane section, but they're asking us for an equation of a line. So we'll just be cognizant of which of the two that you're looking for. So parametric equation for the line that passes through the point. So line that passes through the point 2, -1, 0 and is perpendicular to the plane 2x minus 3y plus 4z, 2x minus 3y plus 4z equals 5. All right, so now let's do some visualization. So in our last problem, at the end of the last video, we had to start off by doing visualization. There's going to be quite a bit of that in this class as you having to try to visualize things. So please be comfortable taking and using little props. You see I use different markers or pens or pencils or paper, cardboard, wrench, whatever I have handy. So please be comfortable doing that to help visualize things, because it helps work out problems. That's the way that I figure out problems, is by doing visualization first. So I have some point P naught, and I'm trying to find the equation of a line that passes through this point and is perpendicular to this plane. So first off, equation of a line tells me I need a point on the line and I need a vector that is parallel to the line. So I'm looking for that capital L that's parallel to the line, because they already gave me the point. So for visualization purposes, we'll make this piece of paper our plane, and then we're looking for the equation of this line that that is perpendicular to this plane. All right, so let's go ahead and put, now I can't necessarily put the point on the plane. I mean, I could, but for sake of argument, I'm not going to put the point on the plane. I'm just saying that this point is somewhere up here in space. This line goes through that point, and the paper is going to be this plane right here. So I'll make this paper that plane. So what do I have so far? I have the point. We'll put my point at the top of the marker. And then I have the equation of this plane. So the equation of the plane, there's something that's inherent in the equation of the plane. Remember, I told you if you're given the equation of the plane in this form, you can automatically see what the normal vector is. So the equation of the line I'm looking for is this black marker. But I have the equation of the plane, which has this normal vector in it. So what do I need to find the equation of this marker? I need a point on the marker, which is right here at the tip, and I need a vector that's parallel to the marker. Well, I can use this normal vector right here. This vector that's normal to the plane is parallel to the marker, right? Because the marker or our line is perpendicular to the plane. So these two things are parallel to one another. So I'm going to use this, which is N for the plane. I'm going to use it as L for our line. So we need, all right, so we're going to use N, which is 2, -3, 4 as our L. So that gives us our L, and we have our P naught. So then the equation, they want parametric equations. So parametric equations, remember, are x equals x naught plus AT, y equals y naught plus BT, and z equals z naught plus ct. So that's x equals, our x naught comes from our point, so 2, and then our a is 2 plus 2t, and y equals -1 minus 3t, and then z equals 0 plus ct. All right, so this is really what we weren't looking for n, but n had worked out for us, so we're going to use n as our L, because that's what we used as for our L, was the n. All right, so next we'll look at number 12 from the same page. So number 12 is a 3-part problem. Says let L be the line. So they gave us a line L, and it's given by the symmetric equations x plus 1 over 2 equals y plus 3 over 3 equals -z. And script P be the plane. So they give us also a plane, and it is 3x minus 2y plus 4z equals -1. All right, part A. Find the point of intersection P naught of L and script P. So find P naught, the point where L and script P intersect. So what you can think about, if you were in a previous math class and you were given just two lines in the plane and you need to find where they intersect, you could do substitution. So you take and substitute the one line into the other line to try to find where the point where the two lines intersect. We're going to do something similar here. So you can do this a couple of different ways. I'm going to use parametric equations, although we're not given parametric equations, just because I think it's the more natural thing to use in the long run. But then I'll show you another way to do this same problem without using parametric equations. So I want to substitute the information from here into here. So I'm going to use parametric equations because I know that I can easily just substitute in an x, a y, and a z very simply. So let's see, what are the parametric equations that correspond to these symmetric equations? So here I have x minus a -1. So that tells me my x naught is -1 and my a is 2. So here I have x equals -1 plus 2t. Then here I have y minus a -3 and my b is 3. So I have y equals y naught, which is -3, and then plus 3t. Now here, be careful with this one because we have to have z minus something. So this negative, I need to bring it down to the denominator as a -1. So this is the same as change that to a positive and put a -1 down there. So this is really z minus 0 divided by -1. So that tells us our z naught is 0, and then our c is -1. So z equals -t. So now I can take, and I can clearly know what x is, y is, and what z is, and I can take those and I can substitute those into this equation up here. So now I have 3 times -1 plus 2t minus 2 times -3 plus 3t, and then plus 4 times -t equals -1. And if we go ahead and simplify this, what we get is negative 3 plus 6t plus 6 minus 6t minus 4t equals negative 1. So that goes away. And then we have the 3. This negative 3 plus the 6 gives us 3. And I'm going to take that 3 and I'm going to move it over to the right hand side. So that gives us negative 4t equals negative 1 minus 3, or negative 4, which gives us that t equals 1. And now what we can do is take that t equals 1, we plug it into these three equations up here, and that gives us the point where this line intersects that plane. That's where those two things would meet. So we're going to take this t equals 1, put it into our parametric equations, and then we'll have our answer to the problem. So now we get that x equals negative 1 plus, we're putting this in right here, so negative 1 plus 2, which gives us 1. Our y equals negative 3 plus 3, so negative 3 plus 3, which gives us 0, and our z just equals negative 1. And now we have the point at which this plane, the plane and the line that we were given, intersect one another. All right, part B of the problem says find an equation of the plane. So find the equation of the plane perpendicular to script L at the point P naught. So now P naught was what we found in part A here. So they want us to call this point right here. P naught is 1, 0, negative 1. And now we're going to use this for part B. Again, find the equation of the plane perpendicular to L at P naught. So find the equation of the plane, and instead of using the names, I'm going to write out the actual equations again. Plane perpendicular to L, and the equations for L, I guess I can use the parametric equations or the symmetric ones. I use the parametric equation just because we can still see, you all can still see those. So find the equation of the plane perpendicular to L. Remember, L is x equals negative 1 plus 2t, y equals negative 3 plus 3t, and z equals negative t. Perpendicular to L at P naught. So really what they mean is just find the equation of the plane that is perpendicular to this line and it goes through that point when they say at P naught. So not that it's perpendicular at that point. That's not what's meant by that. It's meant just it goes through that point. So just a visualization thing again, so we can kind of orient ourselves to see what it is we're trying to do here. I don't think we need this anymore, so let's get that out the way. All right, and let's write out what P naught is, so we don't have to refer to the last problem. P naught is 1, 0, negative 1. So first thing to look at, what are we looking for? Equation of a line, equation of a plane. We're looking for equation of a plane, which means we need a point on the plane and we need a vector that is perpendicular to the plane. So let's say this is the plane, the equation of the plane that we're looking for is this. First, they gave us a point on the plane, and now all we need is a vector that's perpendicular to the plane. So, but this plane is perpendicular to this line. So we're looking for this the equation of this plane. We know that this is the line right here. We know that this line right here is perpendicular to the plane. What do we need? We need a point on the plane. We already have it, P naught. and we need a normal vector. So the normal vector for the plane is what we need, what we're missing right now. We're missing this. So let's see if we can squeeze some information out of this line that we have. So the line, automatically in the equation of a line, inherent is that vector L that's parallel to the line. So the vector L that we have that's parallel to our line is -1, -3, 0. That's parallel to our line. So we already have this vector that's parallel to the line. Now we don't need the line anymore. We have our normal vector and we have our point on the plane. So now we can find our equation of the plane. What is this normal vector? So we're going to use L, which was -1, -3, 0 for n. So now we have our n, and we already had our point right there. So now we just need the equation of the plane, which is a times x minus x naught plus b times y minus y naught plus c times z minus z naught equals 0. And now we can just plug in the information we have. So this is actually our n now. So we have -1 times our x minus our x naught is 1 plus our b, which is -3 times our y minus our y naught, which is 0, and then plus our c, which is just 0. So then we have 0. I mean, this part I don't need to write, but I have it now. So z minus our z naught, which is -1, equals 0. So if you want to, you can simplify these. You don't need to, though. You can leave it just like that. That's perfectly fine. All right, now last part of part C says find symmetric equations of the line perpendicular to script P at P0. So script P was the original plane that they gave us. So they said find symmetric equations of the line perpendicular to So one thing about confusing about this question in the textbook wording is that they're using the names of the line in the plane versus using their equations, but they're doing it to try to make sure that we're paying attention, I'm sure. But that's one of the things you have to be careful of. So I'm going to switch to the equation instead of the name script P or script L or P0. The line perpendicular to script P, and script P was 3x minus 2y plus 4z equals -1. And they say at P0, and P0 was what we found in part A. So that one they had to use the name P0 because otherwise they had to give us the answer for part A, which was 1, 0, -1. All right, so what are we looking for? Equations of a line, meaning we need a point on the line and we need a vector that is parallel to the line. So now, what do we know about that line? That line is perpendicular to this plane right here, and that line contains this point right there. So to make our lives easy, let's make this paper the plane, and this is going to be a point that is on the line, not in the plane, the point that's in the line. So here, this is the equation, this is the line, we're looking for its equation, but we have that line that we have right there is perpendicular to this plane. In the plane, we have its normal vector. We know what this red normal vector is. It is 3, -2, 4. It comes from the equation of the plane. So we know what this is, and because it's parallel. I mean, because they're both perpendicular to the plane, they're parallel to one another. So that means we'll use this normal vector n as our L for the line, and then we're going to use that point right there. So use n equals 3, -2, 4 for L. And now they want symmetric equations. So symmetric equations are let's see, x minus our x naught, which is 1, over our a, which is 3, equals y minus y naught, which is 0. So I'll write it over our b, which is -2, and then equals z minus z naught, which is -1, over our c, which is 4. And you can leave it just like that. Now, some of these things I'm saying leave, if you are looking in a solution manual or something, you have to bear in mind, in all likelihood, they may have simplified. So if you want to check cross-reference your answers with theirs, keep that in mind. So here you might see something like this. I mean, in the solution manual. So say, for instance, they decide to bring the negative up to the top. That might be -y over 2, then equals z plus 1 over 4. All right, and those would be the symmetric equations for the line that we were looking for. All right, so I'll give one more. Actually, we'll stop this here, and then we'll do one more example in the next video, and that'll conclude 11.6.